For centuries, we've been digging into the Earth for, everything. But the next great gold rush, it's not going to be underground. It's up there, among the billions of rocks orbiting our sun. Today, we're cracking open the field guide to asteroid mining.
So, welcome to the high frontier. And look, this isn't just some sci-fi dream anymore. This is the real deal playbook for the next generation of prospectors. We're going to break down exactly how you're supposed to dig, drill, and pull precious materials out of a rock that's just tumbling through the void.
Okay, so here's the big question, right? We've been mining on Earth for thousands of years. We're good at it. But the moment you take that same idea to an asteroid, suddenly everything you thought you knew is completely wrong. What makes digging into a floating rock so incredibly complicated? Before we can get to all the cool futuristic tools for the job, we first have to get our heads around the fundamental physics that are working against us. And trust me, this is where the real challenge begins. When you see it side by side, it's pretty stark. See, on Earth, gravity is your best friend. It holds you, your tools, and all the dirt right where they should be. But in microgravity, there is no down. Any bit of debris you kick up doesn't fall, it just floats away, creating a cloud of dangerous shrapnel. And oh yeah, there's that pesky communication delay, so you can't just fly it with a joystick from back on Earth.
So it all boils down to Newton's third law. Action equals reaction. On Earth, you push on a drill, the ground pushes back. No problem. But in space, if your multi-million-dollar robot pushes a drill forward, the asteroid just pushes your robot backward, sending it drifting off into the black. It's literally like trying to drill a hole while standing on a skateboard. And that right there is exactly why AI is not just a cool feature, it's absolutely non-negotiable. I mean, a signal can take up to 20 minutes to get from Earth to the asteroid. A human operator is totally useless in a crisis. The mission needs an onboard AI, a little brainy sidekick that can react instantly if the drill hits a hard spot or the whole robot starts to float away.
Okay, so now that we know the problems, let's open up the toolbox. First up is the one that feels the most familiar. Good old-fashioned mechanical digging, just, robofied for deep space.
Honestly, the best way to think about this is like gardening in orbit. You're still scooping, digging, maybe even raking, but your garden is a weightless rock pile, and if you're not super careful, all your soil is just going to float away.
So to make this work, you have to solve that Newton problem we talked about. Step one is always to anchor your lander. You gotta latch on with hooks or fire thrusters to hold it in place. Once you're secure, then you can use things like a corkscrew drill for softer stuff, or even a kinetic impactor, which is basically a little jackhammer for the really hard rock, all without pushing yourself away.
But like everything, there's a trade-off. On the plus side, this is based on engineering we already understand. It's pretty reliable for solid, stony asteroids. We call those S-types. The big con, though, it creates a huge mess. We're talking massive dust clouds that can clog up your sensors and coat your solar panels, basically blinding and starving your robot.
Yeah, mechanical mining is messy. So what if you could grab the resources you want without ever even touching the asteroid? Well, that brings us to the next level of tech, contact-free collection. And the idea behind the first method is just beautifully simple. Think about leaving a piece of chocolate out in the sun on a really hot day. That's pretty much the core concept of optical mining.
How it works is you use these giant mirror arrays to focus sunlight into one super intense beam, and you just blast the surface of the asteroid with it. This is perfect for the icy carbon-rich asteroids, known as C-types. The heat turns the ice directly into vapor, and then you just collect it. And the best part? Zero physical contact. That means no mechanical wear and tear at all. And this process is just brilliantly efficient. Step 1, you beam the concentrated sunlight onto the ice. Step 2, the ice vaporizes. It's a process called sublimation. Step 3, you capture that gas with what's basically a super cold trap. And step 4, you process that captured water into hydrogen and oxygen. Hello, rocket fuel. And get this, the potential here is just enormous. If an asteroid is just 10% water by mass, it's basically a giant orbiting gas station. You could create enough propellant to refuel entire missions to the outer solar system, all without having to launch a single drop from Earth's gravity well. That's a game changer.
Okay, so that's water. But what if you're not after water, you're after metal? Well, there's a contact-free method for that too. And the analogy for this one is like fishing for nails in a sandy pond, but with a giant magnet.
For asteroids that are really rich in metals, like iron and nickel, we call those M-types, you can use this incredibly powerful electromagnetic array. You just hover over the surface and literally lift the iron and nickel bits right off the ground. It's super energy efficient, and it creates almost no dust. The only catch? It's completely useless on any rock that isn't magnetic.
So far, everything we've talked about is basically just scraping the surface. But what about the really good stuff, the valuable resources trapped deep inside the rock? Well, for that, you need to get a little more advanced and a lot more aggressive. On the left, you've got what's called thermal extraction, but I prefer its nickname, the space oven. The idea is you heat the rock, maybe with microwaves, until the valuable stuff inside just pops out as gas. On the right, you have chemical extraction, aka the acid bath. Here, you actually inject solvents that dissolve specific minerals, and then you just suck out the resource-rich goop. Here's the deal, though. Both of these methods will get you a ton of material, but they come with huge energy costs and some pretty serious risks. And if you think that's wild, looking even further ahead, we are entering the realm of some truly out-there ideas. We're talking about things like biomining, using engineered bacteria that literally eat rock and excrete pure metal. Or maybe we just grab a small asteroid and spin it so fast that it flings material out, like some kind of cosmic salad spinner. Yeah, these are still just concepts, but they show you just how creative this field is getting. So, okay, we have this amazing toolbox full of robotic shovels, sunbeams, giant magnets, and even space ovens. How in the world does a mission commander decide which one to use? Well, it all comes down to knowing your target.
It all breaks down pretty simply, really. It's totally situational. If your mission is to hit a solid S-type asteroid, your reliable mechanical drills are probably the best bet. But if you find an icy C-type floating out there, it's time to bring out the contact-free optical miners. Heading for a metal-rich M-type? Go with the magnets. It is all about matching the right tool to the right job.
All right, let's run a quick simulation. You're the commander. You've just arrived at an icy asteroid, but your sensors tell you the surface is super fragile. So what do? Do you risk shattering the whole thing with a mechanical drill, or try a magnetic rake that's not going to work? No, you deploy optical mining. You gently vaporize that ice without ever touching the surface. You get your prize, and you leave the asteroid intact. From simple physics problems to some really mind-bending future tech, asteroid mining is, without a doubt, one of humanity's greatest engineering challenges. The resources are out there, trillions of dollars worth of them, just waiting. The only question left is, as we stand here on the edge of this incredible new frontier, are we truly ready to dig deep?